Hello, my name is Hwang. I will present the paper. The title of this paper is Memory Compression Scheme for Mobile Devices. In this paper, we propose a memory compression technique for mobile devices, such as IoT device, sensors, and embedded systems. The characteristics of those mobile devices are low power, relatively low performance, and small size of memory. Through this paper, we are discussing the trade-off problem between space and energy. By using compression method, we can increase the space efficiency. But memory compression requires additional processing overhead and also additional energy consumptions. So a trade-off exists between the space efficiency and the energy efficiency. In this paper, we tried to find a solution to have better efficiency for mobile devices using memory compression method in mobile system. The key issue we're discussing in this paper is the trade-offs between the performance and the power consumption in mobile devices. As we know, the performance of mobile devices include the core clock speed, data rate, operating time, battery cycles, and etc. These performance factors have trade-off relationship with power consumption, and the power consumption affects the lifetime of the mobile devices. Most mobile devices we are discussing here are battery operated, focusing on data processing rate, and shows similar characteristics as real-time devices. Here, considering battery as a key factor in mobile devices, battery saving means extended operating time of a device and slowdown of battery exhaustion means long lifetime of memory device. This figure shows the reduction of battery charging capacity along with the charge and discharge cycles. As we repeat the charge and discharge cycle of a mobile devices, the capacity of the battery decreases and thus the lifetime decreases. This graph especially depicts that the discharge depth is larger, the lifetime of a battery becomes shorter. The discharge depth means the amount of battery discharge before recharging it. In this table, if we recharge the battery after 20% of discharge depth in the charge-discharge cycle, shown as red color, then it shows 3 times longer lifetime compared with the battery which is recharged after 100% of battery consumption. So fully emptied battery charging is negative impact on the battery lifetime. And again, power saving means slow down of battery exhaustion, and in turn that result in device lifetime extension. Our goal is to save power consumption and to extend the lifetime of mobile devices. Historically, in computer science, the space and time have a trade-off relationship. For example, lookup table and recalculation time, or the loop code and the loop unrolling. These examples show the trade-off between memory space and the computation time. Another case, this space and time trade-off can be applied is the data compression. If data is stored in uncompressed way, then it takes more space, but the data access takes less time. On the other hand, compressing the data reduces the amount of space needed, but it will take more time to run the decompression process. In mobile devices, in addition to the traditional space-time trade-off problem, there are trade-offs between power consumption and the space. The space and power, or the space and energy trade-off. So we have to consider the power management problem more seriously in this aspect. Let's consider the space and energy trade-off problem. If we have bigger RAM size, we can have larger space, but we may lose energy efficiency. To gain space by using smaller size of RAM memory, we can use the memory compression technique. By memory compression, we can gain space with smaller RAM requirements. But at the same time, we may lose energy efficiency because there will be the compression and decompression overhead. In a way, memory compression can also have positive impact on the energy efficiency by reducing the space requirement. However, the negative impact caused by the compression and decompression overhead is bigger, we can guess. So, by using memory compression technique, we can gain energy efficiency by reducing memory space, and at the same time, we may lose energy efficiency by adding compression and decompression overhead. So, which is bigger? Efficiency gain by compression or overhead by compression? If we gain more energy efficiency by data compression than losing it by compression overhead, then we can save the power consumption and we can extend the lifetime of mobile devices. One upside is that the compression and decompression consumes power only when demanded, not like the continuous power consumption of SRAM or DRAM memory. So this is the upside. So in this paper, we are focusing on the memory compression scheme for mobile devices to reduce power consumption and thus to extend the device lifetime. The characteristics of our target devices are low data rate, battery-operated sealed devices, and mostly non-rechargeable. That means operating for battery lifetime. Variable data processing for environmental situations like sensing, and roughly predictable data processing load. In those devices, the static energy consumption by RAM space is bigger than the energy consumption by compression overhead. Again, the compression overhead needed only when demanded. In traditional memory hierarchy, the cache memory plays a key role in the memory performance. To get further memory efficiency, compression functions can be added to the conventional memory hierarchy from the processor, L1 cache, L2 cache, and main memory. The compression functions can be located in the memory hierarchy in various ways. For example, the compression function may be located in the L2 cache and under, like shown in figure A. And sometimes there are two different memory partitions with uncompressed data or compressed data. Or the compression function may be located in only memory and no compression on the cache. So there are many researches about memory compression to improve the memory performance. However, this conventional memory hierarchy model is not suitable for embedded or IoT devices, where the characteristics of low power, low performance are in common. So for our target devices, we need some other memory model. In this paper, in the target system of the proposed memory compression method, the processor core directly accesses the memory without cache in the memory hierarchy. For example, we can think a simple IoT sensor node with small size of SRAM. In this model, data are stored in the memory in a compressed form or uncompressed form. And when the processor reads data from the memory, the compression decompression unit runs the decompression process and restores the compressed data and delivers the data to the processor core. This model provides energy gain by small memory space and reduced signaling between memory and processor. At the same time, this model has energy efficiency loss by compression overhead. The device responsible for compression and decompression is called a CDU, compression decompression unit. A CDU consists of a comparator, a compressor, a decompressor, a dictionary for LGW compression algorithm, and a decompression buffer. The decompression buffer temporarily stores decompressed data from the decompressor, and it plays a role like the traditional cache memory by delivering existing data to the processor more quickly. When a data request signal is generated from a processor core, first it checks if the data is stored in a compressed form or in uncompressed form. If data is stored in uncompressed form, that means the decompression is not needed, then the data delivered to the processor bypassing the CDU. If decompression is required, the comparator checks whether the corresponding data exists in the decompression buffer, and if so, deliver it. However, if the corresponding data does not exist in the decompression buffer, it accesses the main memory, accesses the compressed block containing the desired data, reads the value, and transmits it to the decompressor. And after decompression, the restored data arrives in the decompression buffer and the data is delivered to the processor. We performed simulation tests to see whether the energy gain by the compression is higher than the energy loss by the compression overhead. In the simulation, low power simple scalar ARM processor is used, and for the overhead it is assumed that 2 cycles processing overhead is needed and 3 milliwatt energy overhead per word are consumed. This simulation workload, for the simulation workload, my bench embedded benchmark programs are used. And this table shows the instruction counts of benchmark programs. There are several different types of benchmark programs with various instruction counts. This figure shows the space gain by memory compression. Compared with the existing scheme without compression, our proposed system shows result from 9% to 15% of space gain by compression. This have positive effect on the energy efficiency. The next figure shows the difference of computation time caused by memory compression. Compared with the case without compression, it shows from 5.2% to 6.9% of computation overhead caused by the compression-decompression process. These results have negative effect on the energy efficiency. This figure shows the normalized IPC value for each benchmark program. The instruction per cycle of the existing system on the left and the proposed system on the right. the average IPC value was reduced by 5.7%. However, despite the energy loss by the compression overhead, the total energy efficiency is positive in all simulation cases, improved up to 1.6%. And please note that this improvement of energy efficiency is calculated for the same size of data. Considering the 10% of space gain by data compression, we think the actual advantage of the proposed method is even bigger. The power consumption reduction for the benchmark programs, that means the energy efficiency with data compression, are on average 10% higher than that of the existing system without compression. So we can say that memory compression techniques have positive impact on the energy efficiency of our target mobile environment. In conclusion, although memory compression is not recommended for every case, but it can be effective for our target systems where space can be traded with energy consumption. By reducing static energy consumption of RAM but increasing compression decompression overhead consumed only demanded. It can be very useful for some cases, including lifetime serial sensors or sealed devices for tough environments such as deep sea or desert. That is all my presentation. Thank you for watching.